Okay, so what we're going to talk about today has to do with pretty much grabbing everything we've learned in this chapter and extending to, topics that have to do with business and econ and so on. So our goal is going to be to maximize certain things, like such as the cost or minimizing cost and maximizing profit, and so on. So just to quickly put this, the goal of today is to work with equations such as cost or profit and revenue. And basically, we want to use these equations. And we want to use these equations to minimize or maximize each. Okay, it all depends on which function we're talking about. Obviously, for profit, we'd want to maximize. For cost, we'd want to minimize it. So before we kind of get into finding these equations and their derivatives, let's kind of start defining some of these things. So the first function we're going to talk about is the cost function. And the cost function, we know that it's denoted as C of x. This is the cost required to produce x units of some product. So our focus is going to be, well, what's the cost in us producing X units of this product? So kind of that's what we're gearing ourselves towards. Okay, so the next thing we're going to define is the marginal cost. Now, we may not have talked about marginal cost in this class, but marginal cost is simply just finding the derivative of the cost function. So anytime you hear marginal something, that's where we're trying to find the derivative of that function. So if I ever say find me the marginal cost, we're literally talking about finding the derivative of the cost function. So by definition, the marginal cost is the rate of change of C of x, which is basically our cost function. So what does this imply? What we're saying is that marginal cost equals to C prime of x. Okay, so before we move any further, I kind of want to give us a typical idea of what the graph of the cost function usually looks like. Now, it's not like this for every case, but usually we should expect a typical graph of a cost function, C of x, should pretty much have kind of like this characteristic. So if I have a function, so of course we have our fixed costs in the beginning, and then it usually tends to have this type of a look to it, where this right here shows that we have a point of inflection. So let's kind of make some comments about the graph of C of x, which, we could kind of make sense of why it has this pattern. See, in the beginning, of course, the more product you produce, your cost goes up, but at first it doesn't increase as quickly because we're basically being more efficient with our fixed costs. And then after a while, you kind of get your inefficiencies of your product or whatever it is that you're producing, and then your cost starts increasing at a much quicker rate, which kind of gives us this point of inflection. So let's make some comments about this graph here, and then we'll kind of go on with the rest of this section. So some comments here based on this graph. So the first comment is that, of course, we know that C prime of x is the slope of the tangent line to C of x at each x comma c of x. So this is kind of nothing new to us. You know, when you find the marginal cost, you're finding the slope of the tangent to this curve at each x value. Okay, so the next comment is that, which I kind of already mentioned, what we notice is that the cost function initially, or is initially, concave down. Now the reason why it's concave down is because there is more efficient use of fixed costs of production. So basically kind of what we mentioned, we're putting these initial costs to use more effectively. And, you know, in econ class, this is known as the economies of scale. Okay, so if you have taken economics, you've probably heard of this term. And then what we notice is, let's move on to the next page. So then the next comment is, then we notice that we hit an inflection point. So there is an inflection point. And then the cost curve is concave up. And what's happening there, the reason why it's concave up is that our marginal cost starts increasing. So, and the marginal cost is increasing. Okay. And then this basically has to, and the reason why kind of these happen is sometimes when you overproduce or you try to produce more of your product, what that forces us to do is sometimes you have overtime costs for employees, you know, inefficiencies of large, and such as, you know, inefficiencies of large scale operations. So these are kind of like the contributing factors as to why our cost function all of a sudden has that steep increase or that sudden increase after the inflection point. Because of course, if you start producing much more product and then you start hitting certain inefficiencies, which kind of causes the cost to go up. Okay, so let's move on to the next topic or the next function, which is called the average cost function. And the name itself pretty much tells you what it is that we're doing, right? The average cost function is pretty much taking the cost per unit, or on average, how much it costs for you to produce each unit of your product. So this, by definition, is the cost per unit when X units are produced. And I'm sure you could even come up with the formula for this, because if I'm trying to find the cost per unit, what do I need? We take the entire cost divided by however many units we produce, and that'll give us the average cost per product. So I'm going to just stay consistent with the book. So the lowercase c of x, so capital C is our cost. Lowercase we're going to use for average cost. So obviously average cost, which this is our average cost, equals to the total cost divided by however many units. Okay, so basically what you should notice is that the typical graph of the average cost function looks like this. So in the beginning, what you notice is to reduce your average cost, you have to start producing more of your product. So what will happen is initially you kind of have a vertical asymptote here, and then the more you produce of your product, the average cost goes down. But then at some point, you hit your minimum, and then the average cost starts rising up again. So what you should notice is that the typical average cost function looks like this. And see, what we want to do is we notice that this has a minimum somewhere, and our goal is to minimize our average cost, right? For obvious reasons. We don't want to pay more to produce each product. We kind of want to find where is this minimum here, and let's minimize it. So let's talk about finding the minimum of the average cost. And see, this you guys should be very good at. So finding the minimum of average cost function. So in fact, let's kind of take a step back and go back to your average function, or average cost function, which is this guy. If I said minimize this, how would you minimize it? See, we should be really good at finding maxes and mins up to by now. So if you want to minimize this, I'm sure you've already said it, the first thing you'd want to do is find a derivative of this. So let's find a derivative of that. So the average cost function's derivative, which since it's a quotient function, we'll use the quotient rule. So it'll be the derivative of the top times the bottom. So it'll be x times c prime of x minus the derivative of the bottom, which is just 1 times c of x all over the bottom squared. So then to find our average, to minimize this, we need to set this equal to 0, which if I do that, let's go to the next page, we get x c prime of x minus c of x equals to 0. So what I did from the previous step, I just multiplied both sides by x squared. Now I'm just trying to minimize this. And then, and by the way, this should be a lowercase c, just to kind of make a point here. Capital C is cost, lowercase c is average cost. So what does this imply? We get lowercase c prime of x. When I solve this, I get what? C of x over x, which look at how interesting this looks. What did I get? To minimize my average cost, what do I notice? My marginal, or the derivative of, oh, sorry, actually this should be a capital C prime of x, sorry. So this should be C prime of x, because this C prime of x is actually coming from here, right? The lowercase c prime I'm setting equal to 0. So maybe I should say let's lowercase c prime of x equal to 0. So actually we start getting something really interesting out of this, because what do I notice here? To minimize this in some sense, or if we have a minimum of our average cost, what's capital C prime of x? Isn't that my marginal cost? So what do you notice? Your marginal cost equals to your average cost. So here's what we could say. We would say that if the average cost function is a minimum, then what is it that we know? What do we just show? The marginal cost will equal to the average cost. So what we could say is the average cost equals to the marginal cost. So we actually get something really nice out of this. We just noticed, like, hey, if we know that we have a minimum at the average cost function, then the marginal cost set equal to average cost, marginal equals to average, that would give you pretty much our minimum. Now, one comment I want to make here is that how do we know if we've minimized? Well, we can use the first derivative or second derivative test. So we can say to ensure this is a minimum, we can either use first or second derivative test. Don't use both, because remember, the first is a little longer than the second. So if you can use the second derivative test, which would make things a lot quicker, you could use that. But if not, then you'd have to use the first derivative test. But basically, remember, if you know that the average cost is minimized, then you know to minimize the average cost, just take the average cost, set it equal to the marginal cost, and that'll get the job done. And then we just pretty much proved it here. Okay, so moving on. Let's talk about the demand function. So we've dealt with the demand function in pre-calculus, and so we'll talk about it again. So if P of X is the price per unit that the company can charge if it sells X units. So one thing I want to point out is this is what's called the demand function. So then P of X is the demand function. So one thing I want to point out to you that's a little weird about the demand function, people usually get confused by how the demand function works. See, the demand function, the way it's set up is it says, look, you tell me how many units you want to sell, then this equation will tell you what you should set the price as. So one common mistake people usually make, they think that the demand function is designed in a way where you put the price and it'll tell you how many units you'll sell. It's actually the other way around. So what you're saying is, this says, look, you tell me how many units you want to sell, and this equation will tell you what the price should be set at. Okay, so that's what we mean by the demand function. So pretty much, you tell me the units you want to sell, and this equation will tell you the price that you should set it at. So that's our demand function. So with that said, let's move on to the revenue function. So the revenue function, once again, this is how much money you get in total. So this is if X units are sold and the price per unit is P of X, which is pretty much what our demand function is, right? That's where we're getting the price from. Then the revenue function, R of X, is defined as R of X equals to P of X times X. So X times P of X, which makes sense to us, right? Because revenue is how much money you get. So P is the price in which you're selling your product. X is how many you sell. So X times the price, or how many you sell times how much each product is, that will give you your revenue, which is how much total money you get back. Okay, so with that said, let's define marginal revenue, which by now I'm sure you can guess what marginal revenue is because we talked about this, right? So marginal revenue is literally the derivative. So the marginal revenue function is simply the rate of change. So this is the rate of change of the revenue function with respect to the number of units sold. So in other words, what are we saying here? The marginal revenue, this is in other words saying this is the derivative of the revenue function. So in other words, it's just r prime of x. So if you have the revenue function, then you could find the marginal revenue, because literally we want to find its revenue, the derivative of the revenue. So moving on to the profit function. See, the revenue function is nice, but you could probably tell me why the revenue function isn't something that we'd rather work with. Because look, if I were to tell you, hey, I own a company, and last year the revenue of my company was $5 million. So does that mean that, I'm making a lot of money and, like I'm a millionaire? See, what would your next question be to me if I told you that, hey, look, I'm the owner of a company and my revenue is 5 million for this last year? And I'm sure you've already thought about it, but your next question should be, well, what was your cost? And if I tell you, oh, the cost of operating my company was 6 million, then what would you say? Well, then you'd say that I'm pretty much a big loser here because I've lost $1 million. Sure, my revenue was 5 million, but I lost more. The cost of operating was more than my revenue. So what we actually care for beyond revenue is the profit function. So we're going to turn our attention to the profit function, which pretty much the profit function says this is the defined as cost subtracted from revenue. Okay, so in other words, my profit is R of X minus C of X. So obviously, since this is the case, we want to now talk about the marginal profit function. And I'm sure you've already guessed, this is the derivative of the profit function. And see, what's our goal? Our goal, which, by the way, let's write this out, P prime of X is just literally R prime of X minus C prime of X. So obviously, what's our goal? When you own a company, what do you want to do to your profit? You want to maximize it. So if you want to maximize profit, once again, think back to the earlier sections. How would you maximize profit? You'd first find its derivative, which is finding the marginal profit. And then what do? We take the marginal profit and set it equal to 0. And once again, we're going to notice that something very interesting happens, okay? So by doing so, we would say, look, maximizing profit, what would we do? To do this, we take the marginal profit. So we're going to set the marginal profit equal to 0 and solve. And notice what happens. So once again, we get something really, really nice out of this. So if I take P prime of X and I set it equal to 0, what does that yield? That yields R prime of X minus C prime of X equals to 0. And so what does this imply? If I add the marginal cost of both sides, I get R prime of X equals to C prime of X. And so what do you notice here? If profit is maximized, see, when you have R prime of X equals to C prime of X, that doesn't guarantee that my profit is maximized. But what we could say is this: if we know that our profit could be maximized, then that means the marginal revenue should equal to the marginal cost. So this is what we're going after once we know that our profit could be maximized. So here's what we could say. If the profit is a maximum, then marginal revenue equals to marginal cost. So remember, and I'm sure this already makes sense to you, just because my derivative, which is P prime here, equals to 0, we're not guaranteed to have a maximum or a minimum, right? Remember, where your derivative equals to 0, those are your potential maxes and mins. So notice how in my wording here, I'm very, very careful. I say, look, If the profit is a maximum, then I know for a fact that my derivative, my P prime equals to 0, which if the P prime equals to 0, then here it shows that the marginal revenue equals to the marginal cost. So just as always, how do I make sure that just because my profit equals to 0 or my marginal profit equals to 0, how do I ensure that this is truly maximized? We could use the first derivative test or the second derivative test. So that's why I kind of write this comment out here. So to ensure this is a maximum, use the first or second derivative test. Okay, so that's basically what you need to always do. So if you're trying to maximize profit, it's good that you find the zeros of your marginal profit, but you also need to make sure that you check and see it is maximized, just like we've done for all the other, especially when we graphed functions and we want to find local maxes and mins, okay? So look, I know I didn't do any examples. This section is just simply finding a bunch of derivatives and maximizing or minimizing. So that you should be pretty good with. The main focus with this section is basically the terminology. So I'm pretty confident that you should be able to do the problems, and we are going to work on them in class anyway. So, if you have any questions, feel free to ask. But this section was strictly, if you noticed, if you have taken econ, none of this should be new to you. The only new aspect is now we're mixing calculus with econ, which is supposed to kind of simplify things for us. So, on homework, when you're reading this or when you're working on the problems in class, if it's to say find the marginal revenue, at least you know through these notes what the definitions mean. Okay, so that basically takes care of this section. If you have any questions, feel free to ask me and I'll be more than happy to answer it in class.